As physicists, we've enthusiastically guessed this for over a century. Starting around 1916, this occasion marks a momentous accomplishment, offering a brief look into one of the universe's most captivating and cryptic peculiarities: dark holes. These grandiose monsters, known for their enormous influence, remain extraordinarily elusive. While they are epic in terms of their gravitational impact, they are nearly undetectable, making them even more puzzling. One such dark hole, possibly weighing between 2 to 4 million times the mass of our Sun, may be the subject of this discovery. Over the past several decades, research devoted to dark holes has transformed our understanding, taking us from a place of absolute ignorance to one where we are beginning to get a close look at them. And now, things have taken an even more thrilling turn, as physicist Michio Kaku has revealed that we have finally figured out how to look inside a dark hole. This discovery opens the door to a wealth of new information that could illuminate aspects of science we may have previously overlooked. Let us take a deep dive into the realm of dark holes and uncover what exists within them. While space is limitless and vast, the concept of dark holes raises endless questions. Before we dive into the specifics of Kaku's remarkable findings, it's essential to understand the basic nature of dark holes. Most people have a general understanding of what dark holes are, yet significant gaps in our knowledge remain. The theory of dark holes dates back to 1916 when Albert Einstein published his general theory of relativity. This theory predicted the existence of dark holes, though at the time, the idea was purely theoretical. It wasn't until about 50 years later, in the 1960s, that substantial evidence for their existence began to surface. Researchers studying the constellation known as Cygnus observed an unusually bright blue star emitting X-rays. This star, they discovered, was not stationary but orbiting a massive dark object. Upon further examination, it became clear that these X-rays were being drawn into this object, leading to the coining of the term dark hole. This discovery was a monumental turning point, confirming that dark holes were not just a product of Einstein's imagination, they were real, tangible entities that existed in space. It became clear that we needed to study them more thoroughly. Scientists from around the world began focusing their research on a specific dark hole in the Cygnus constellation, designated Cygnus X1, which lies approximately 6,000 light-years from Earth. This dark hole was millions of times brighter than the Sun and exhibited extreme density, with a gravitational pull so intense that not even light could escape it. This was the primary characteristic of a dark hole, the ability to trap light within its gravitational embrace. The nature of a dark hole is both fascinating and terrifying. A dark hole is a region in space where gravity is so strong that nothing, not even light, can escape it. Any object that ventures too close to a dark hole is sucked in, and once it passes a critical boundary, it is lost forever. This inherent danger is why it is crucial to expand our understanding of dark holes. After the discovery of Cygnus X1, researchers launched an extensive search for other dark holes. Current estimates suggest that there may be over 100 million dark holes scattered throughout the Milky Way galaxy. However, due to their nature, these cosmic giants are incredibly difficult to detect, meaning we do not have an exact count. What is clear, however, is that there could be millions of dark holes within our galaxy, highlighting their significance in astronomical research. The main concern surrounding dark holes revolves around their gravity. Their gravitational force is so immense that anything getting too close is gradually compressed to an extreme degree until it becomes a singularity. Simply put, dark holes function as cosmic vacuum cleaners, pulling everything in with an insatiable force. One of the most unsettling aspects of dark hole research is that if someone were to fall into one, they would be stretched into a long, thin shape due to the tidal forces acting upon them. This stretching would occur gradually, and the individual would perish before reaching the final stage of this process. So, to be clear, it's best to avoid falling into one at all costs. Although the nearest dark hole is about 500 light-years away, it still raises questions about the potential dangers they pose to us. In 2021, a remarkable achievement was accomplished when scientists successfully captured the first clear image of a dark hole. This particular dark hole was located in the M87 galaxy. The research team took multiple images over several nights, and by stitching these images together, they created a comprehensive photograph that revealed stunning details. It turns out a dark hole is not just a giant void of nothingness, as many people assume. In fact, a dark hole consists of 3 distinct layers. 1. The event horizon. Once an object crosses this boundary, there is no turning back, it will inevitably be pulled into the dark hole. 2. The photon sphere, a region where light itself can be trapped in orbit around the dark hole. Any light entering this area becomes trapped by the dark hole's gravitational force, unable to escape. 3. The singularity, the point at which everything that falls into the dark hole is crushed down to an infinitely small point. This is where the laws of physics, as we know them, completely break down, making it impossible to predict what happens next. What's even more intriguing and alarming is that no two dark holes are exactly alike. While they all follow this three-layer structure, their behavior can vary significantly. Typically, scientists rely on telescopes to observe celestial objects. However, when it comes to dark holes, this method is impractical because they are invisible. Scientists study them indirectly by observing the radiation they emit, as well as the surrounding gas and dust. Sending probes like Voyager to explore a dark hole is not feasible, as anything crossing the event horizon would be pulled into the singularity and destroyed. Consequently, scientists must study these extraordinary objects through a two-dimensional lens despite their inherently three-dimensional nature. One theory regarding the formation of dark holes is that they result from collapsing stars. When a star exhausts its fuel, it can no longer generate the energy needed to counteract gravity, leading to an inward collapse that can ultimately create a singularity. To further investigate the nature of dark holes, NASA scientists turned their focus to the core of the M87 galaxy. Here, astronomers observed a massive vortex of superheated hydrogen gas spinning at an incredible speed of 1.2 million miles per hour. The sheer force of this spinning gas should have caused it to disperse, yet it remained intact. Scientists theorized that an enormous mass at the center of the galaxy, weighing between 2 to 3 billion times the mass of the Sun, was holding everything together. This mass could only be explained by the presence of a dark hole. However, dark holes may not just be created by collapsing stars. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe the dynamics of a rotating dark hole. Kerr's solution suggested that instead of collapsing into a single point, a rotating dark hole would form a thin disk, a phenomenon known as the ergosphere. The ergosphere is a region surrounding the dark hole where the laws of physics begin to break down. Kerr's solution also predicted the existence of an Einstein-Rosen bridge, commonly known as a wormhole. This hypothetical passageway would connect two separate regions of spacetime and, in some theories, could even link parallel universes. If someone were to fall into a dark hole, rather than being crushed, they might travel through this wormhole and emerge in a different universe or even at a different point in time. To understand how a wormhole works, we must first grasp the concept of spacetime. According to Einstein's theory of relativity, space and time are intertwined, forming a four-dimensional fabric. Objects with mass distort this fabric, creating a gravitational field that causes other objects to move toward them. Imagine spacetime as a sheet of paper. If you place 2 points on it and draw a line between them, that line represents the path objects take through spacetime. However, if you could fold the paper, you would create a shortcut between the 2 points, much like a wormhole connecting two distant regions of spacetime. Wormholes are not just science fiction. They are a direct prediction of general relativity. However, no one has observed one yet. Intrinsically temperamental, wormholes can implode very quickly. The potential for wormholes to act as movement pathways through existence has spellbound physicists for a long time. While the idea of crossing immense distances in a moment or venturing through time is unquestionably thrilling, the difficulties are impressive. Einstein's special theory of relativity predicts that nothing can travel faster than the speed of light, which places an absolute limit on the plausibility of wormhole travel, at least with our current understanding of physics. Lately, a specific kind of wormhole known as the CPT wormhole, after Royer, has captured the imagination of many. This speculative wormhole would connect two distant points in spacetime, potentially even linking different universes or different moments in time. However, critics argue that the CPT wormhole may be unstable or impossible to traverse due to extreme radiation and quantum-level forces. Some physicists point out that Einstein's equations, which describe black holes and wormholes, do not account for the quantum forces that govern subatomic particles. To fully understand these phenomena, a new theory that unifies quantum mechanics with general relativity is required. Such a theory, known as a theory of everything, could explain how the universe functions at every scale, from the smallest particles to the largest cosmic structures. Michio Kaku, a leading theoretical physicist, has been working on this unified theory for decades. One promising candidate is superstring theory, which proposes that all fundamental particles are actually tiny vibrating strings. In this framework, the universe is seen as a symphony, with different particles corresponding to different vibrations of these strings. Superstring theory also provides possible explanations for black holes, wormholes, and other exotic phenomena by demonstrating how strings warp the fabric of spacetime. Despite its promise, superstring theory remains highly speculative, as it requires extra dimensions of spacetime that we cannot yet directly observe. These extra dimensions could be so small that they are effectively invisible to us. Some theorists suggest that these dimensions were more prominent at the beginning of the universe, during the Big Bang, and later collapsed as the universe expanded and cooled. The potential of superstring theory to explain black holes, wormholes, and the very fabric of the universe remains one of the most exciting frontiers of modern physics. As we continue to unravel the mysteries of spacetime, black holes, and the universe itself, it is clear that there is still much to learn, perhaps even more to discover, about the fundamental nature of reality. As we stand on the brink of such groundbreaking discoveries, one key realization remains. We are only scratching the surface in understanding black holes and their true nature. Michio Kaku's work in the field of string theory and quantum gravity has only begun to offer potential answers. Even though we have managed to gain a clearer picture of black holes through technological advances, such as the Event Horizon Telescope and new indirect observation methods, many aspects remain beyond our grasp. The frontier of theoretical physics, particularly regarding black holes and spacetime, remains an incredibly active area of research, where much speculation and exploration await. Beyond their obvious role in shaping spacetime, black holes have become central to discussions about the origins of the universe itself. String theory suggests that cosmic collisions could lead to the creation of new universes, and black holes could play a crucial role in this process. Such a theory implies that our universe may have been born from the collision of two previously existing universes, or perhaps even that we live inside a black hole. If this idea proves correct, it could challenge everything we assume about the Big Bang, and we might begin to see black holes not just as destructive forces but as potentially creative ones, gateways to other realms or parallel universes. While the idea that black holes could serve as portals to other universes or provide insights into time travel is tantalizing, it remains within the realm of theoretical speculation. The mechanics of wormholes and the ability to navigate through them remain significant mysteries. Even if wormholes were stable enough to form, the extreme radiation and forces near these structures would likely make them impassable. Some physicists speculate that if we could stabilize a wormhole, it could theoretically allow travel through time or between distant points in the universe. However, this remains a distant dream, given our current technology and understanding. When we examine black holes through the lens of quantum mechanics, we encounter even more perplexing questions. The behavior of particles at the quantum level is fundamentally different from what we experience at macroscopic scales. The laws of physics appear to break down completely when we consider objects like black holes. This discrepancy between quantum mechanics and general relativity has been one of the greatest challenges in theoretical physics. Theories such as superstring theory offer a possible framework for reconciling these differences by introducing extra dimensions and providing new insights into the nature of gravity. However, this theory has yet to be experimentally confirmed, and many of its predictions remain untested. Theoretical physicists like Kaku are working tirelessly to unify these two major pillars of physics, quantum mechanics and general relativity, into a single unified theory that can explain the full spectrum of phenomena across all scales. A theory of everything would not only provide a deeper understanding of black holes and other exotic objects in the universe, but could also illuminate the very nature of spacetime itself. The concept of extra dimensions, as predicted by string theory, may help explain the hidden forces that govern the universe. It suggests that what we perceive as a four-dimensional reality may actually be just a small slice of a much larger and more complex structure. Another area of intense study is the role black holes play in the evolution of galaxies and the larger structure of the universe. The discovery that supermassive black holes exist at the centers of most galaxies, including our own Milky Way, raises further questions about their influence on galaxy formation, star birth rates, and even the ultimate fate of the universe. The idea that black holes could play such a fundamental role in shaping the universe adds another layer of complexity to their already mysterious nature. Moreover, the intense radiation emitted by black holes, known as Hawking radiation, named after the renowned physicist Stephen Hawking, has led to fascinating discussions about the ultimate fate of the information that falls into a black hole. For decades, Scientists have debated whether information is lost forever when it crosses a black hole's event horizon, a concept known as the information paradox. Hawking's groundbreaking work suggested that black holes could emit radiation that gradually causes them to evaporate over time, potentially resolving the paradox. However, this remains an active area of research with no definitive answers yet. What is clear is that the study of black holes has not only provided profound insights into the nature of gravity, spacetime, and the universe as a whole, but has also opened the door to a new frontier in physics. Black holes challenge our understanding of the laws of nature and continue to provide fertile ground for new theories and discoveries. As our observational tools improve and as we delve deeper into the quantum and relativistic realms, we are likely to uncover even more profound truths about these enigmatic cosmic objects. The journey of exploration, like the mysteries of the universe itself, is bound to take us to places we have never imagined. As we push the boundaries of our understanding, new questions emerge. If black holes can act as cosmic engines shaping galaxies, could they also influence the fundamental nature of time itself? Some physicists propose that black holes might store information about the past, effectively preserving a record of the universe's history within their event horizons. This idea ties into the ongoing debate about the information paradox. If information is not lost within a black hole, where does it go? One hypothesis suggests that information could be encoded on the event horizon itself, a concept known as the holographic principle. This theory, pioneered by physicists like Gerard T. Hooft and Leonard Susskind, proposes that all the information contained in a three-dimensional region of space could be stored on a two-dimensional surface. If true, it would mean that our entire universe might function like a giant hologram, where reality as we perceive it is merely a projection of underlying quantum information. Furthermore, if wormholes can exist as stable structures, they might not only serve as cosmic shortcuts but also as information channels. Some researchers speculate that quantum entanglement, a phenomenon where two particles remain connected across vast distances, could be linked to microscopic wormholes, forming what is sometimes called the ER equals EPR conjecture, named after Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement. If this conjecture holds, it could suggest a deep connection between spacetime geometry and quantum mechanics, potentially leading to breakthroughs in understanding gravity at the smallest scales. The future of black hole research. With advances in observational technology, such as next-generation space telescopes and gravitational wave detectors, scientists hope to gain even more insights into black holes. The James Webb Space Telescope, JWST, has already begun providing unprecedented views of the early universe, while the Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will detect low-frequency gravitational waves emitted by merging black holes. These tools will help answer some of the most pressing questions in astrophysics, including how black holes evolve and whether they can truly act as bridges between different regions of spacetime. Meanwhile, laboratory experiments in quantum mechanics are also shedding light on the mysteries of gravity. Some physicists are exploring the possibility of creating artificial black hole analogs using Bose-Einstein condensates, ultra-cold atoms that mimic certain aspects of event horizons. These experimental setups could help test some of the predictions of quantum gravity in a controlled environment. Could black holes be the key to a new understanding of the universe? As research continues, some scientists are beginning to entertain even more radical possibilities. If black holes can be linked to the birth of new universes, could it be that each black hole in our universe leads to another cosmos? This multiverse hypothesis suggests that every time a black hole forms, it might create a new universe on the other side of its singularity. If true, our own universe could have originated from the collapse of a massive star in another universe, leading to a seemingly infinite chain of interconnected realities. Additionally, theories like loop quantum gravity propose that singularities, the infinitely dense points at the center of black holes, might not actually exist in the way general relativity predicts. Instead, quantum effects could prevent spacetime from collapsing entirely, allowing for a bounce effect that leads to the formation of new cosmic structures. The ultimate question: what lies beyond? Despite these incredible theoretical advancements, one fundamental question remains unanswered: what happens beyond the event horizon of a black hole? Our current understanding suggests that the laws of physics as we know them break down inside a black hole, but whether they give way to a singularity, a wormhole, or even another universe remains unknown. If future research can merge quantum mechanics and relativity into a complete theory of everything, we might finally unlock the secrets of black holes, spacetime, and the very foundation of existence itself. Until then, Black holes will continue to serve as nature's most enigmatic laboratories, testing our understanding of reality in ways we never imagined possible.